Hi, my name is Flora, and I'm a current senior at California High School. And today I'll be talking about the scalable formal synthesis of plus etomoxir without pyrophoric reagents enabled by a one-flask tandem aldol-Luche sequence. So in this talk, I'll be first going over what the CPT-1 system is and what etomoxir is, followed by our project goals, current efforts in optimizing synthesis and computational modeling, and finally, future efforts. The CPT1 is a enzyme located in the um, outer membrane of the mitochondria. CPT1 forms acyl carnitines from long-chain fatty acids and carnitine, where it is then transported through the inner mitochondrial membrane through CPT2, where it's turned into acyl-CoA. In other words, it's the rate-limiting enzyme for fatty acid oxidation. Now, for um, and for diseases where fatty acid oxidation metabolism is crucial, such as type 2 diabetes, inhibition of the CPT1 system can treat dysfunction in fatty acid metabolism. In fact, many small molecule inhibitors have been developed as a way to treat diabetes, including the one shown on the screen here. These molecules range from natural products such as GHPB and teglicar, which is a carnitine type molecule. While many of these molecules have shown to effectively inhibit CPT1, they have failed phase 2 clinical trials due to off-target toxicity. Another small molecule inhibitor is etomoxir. Etomoxir works through three main structural components. First, the arrow ring, where it pi stacks with a key histidine residue in the binding pocket. Next, the carbon chain, which mimics a lipid to allow it to enter the enzyme and then keeps it in place in the binding pocket. And finally, the alkylating group, where the stereochemistry of this epoxide is extremely important to how the molecule functions, where the other phase epoxide is inactive in inhibiting CPT1. This alkylating group binds to the cysteine residue in an irreversible fashion. Here you can see how the cysteine 304 residue binds to etomoxir covalently. The thiol on the cysteine 304 residue is the nucleophile in this group, and it performs the SN2 type reaction, where it fills the sigma star orbital between the CO bond, where it then breaks this bond and then forms this molecule that's covalently binded in the enzyme. This is a preliminary docking model where you can see the two pi bonds right here, these two, where they're overlapping in a pi stack aromatic ring type fashion, and then you can see the alkylating group right here, and then here's cysteine. It's not covalently binded in this pose, which I'll talk a little bit about later. While etomoxir showed effective irreversible inhibition of CPT1, it also caused hepatotoxicity and a lack of selectivity, which caused to its early cancellation of phase 2 clinical trials due to its poor pharmacokinetic properties and narrow therapeutic window. However, our lab is still interested in this molecule due to its analog. This analog is the only difference between this analog and etomoxir, as you can see, is the arrow ring, where instead of the chlorine group at the 4 position on the arrow ring, there's 2 nitro groups at the 2 and 4 position. This analog, with the only difference being the arrow ring, has shown lower toxicity and higher selectivity between CPT1A, the liver form isoform of CPT1, and CPT1B, which is the muscular form. This allowed us to design and come up with an analog library where we would use possible arrow fragments, which is shown over here, where we change the bulk and the electron withdrawing properties of the fragments on the arrow ring and develop a structural activity relationship between the arrow ring and the selectivity and inhibition of CPT1 through these analogs. And that would answer our question of whether or not changing the arrow ring can alter etomoxir's toxicity and result in more selective analogs. To synthesize these molecules, we need to first create a synthesis route where we'd have a late stage intermediate where we could easily access analogs from. Previously reported in 2004 was the synthesis route you can see on the right, where it first starts with commercially available 1.0 5-bromopentanol, where it is first protected with a TIPS group using TIPS chloride and imidazole, followed by homologation using MBO and TMED, and then sharpless epoxidation to form the forward-facing epoxide, and then ruthenium-3 catalyzed sodium perrite oxidation and esterification, then deprotection to form 1.5, coupling to, and finally Medicinal coupling to form the analog, the 2,4-dinitro analog 1.7. This intermediate 1.5 to this final compound 1.7 goes through one step between this intermediate and this intermediate of adding the arrow ring. To access this 1.5 molecule, though, we'd have to go through a couple. This route is through this route, we'd have to go through a couple hard steps, especially this second step right here, from 1.1 to 1.2. This step uses mbutylithium. If you don't know, mbutylithium is pyrophoric, which basically means that it ignites on fire with the littlest bit of air, and like even 1 part per million air will light it, will ignite it. And along with its long reaction time being 18 hours and the danger of the chemical, we'd have to constantly monitor it. And as high school students, we can't really do that as it's not really a option for us. Alongside that, the transfer of multi-grams of this material is extremely tedious, with needing to have everything under inert gas and making sure that everything is very sealed. And this causes it to be hard to access the intermediate 1.5 that I was talking about earlier with ease. To come up with another synthesis route, we had to first do some retrosynthetic analysis, where we had to look through the mechanism of how this bond was formed and how this molecule is synthesized. This molecule is formed through a lithium dianion addition, where it forms this carbon-2 and carbon-3 bond, where it first takes methyl alcohol and we treat it with 2 equivalences of MBE. This deprotonates to form the dianion, which forms this resonance structure shown on the top right. Through single electron transfer, it forms this bromine radical and the methyl alcohol radical. This bromine radical is not extremely stable, so it then immediately forms the carbon radical, where it goes through radical addition to form this carbon-carbon bond highlighted in blue. Then through acid workup, you get your product, which is this sharpless epoxidation setup. In our proposed synthesis, we first start off with 2.0, which is a commercially available diol, octane diol, and we desymmetrize it with monosilylation using TIPS triflate and sodium hydride. Followed by that, we use oxidation using Des-Martin conditions, followed by aldol catalyzed by pyrrolidine and formaldehyde, and a Luche reduction. Following that, we'd use the same conditions as previously mentioned: sharpless oxidation and esterification, deprotection, and finally Medicinal coupling. In this route, instead of going through that mbutylithium step, we instead use this aldehyde, this primary aldehyde 2.2, and through that we use aldol condensation followed by a Luche reduction to form this 1.2. This reduces the through tests, we are able to reduce the reaction time from 18 hours to about 2 hours on 250 milligram scale, and it also removes the pyrophoric reagent. This allows for greater scalability. We were able to design this route through, as I was saying earlier, a bit of retrosynthetic analysis, where this bond is where the carbon-2 bond, this methylene bond, is formed via aldol condensation, where you can see in this on the right side of the screen the mechanism of action, where the pyrrolidine acts as a catalyst to form this very this electrophile, this very good electrophile and this not so good nucleophile. Which forms this complex over here, and followed by that pyrrolidine leaves, and then hydrolysis causes the other pyrrolidine to leave, which forms this alpha beta unsaturated aldehyde, which then through reduction conditions, we can form the alcohol, the desired alcohol. Another way we came up with was putting all the using a prolidine and prolinol type epoxidation catalyst, where we take our previously our one pot and add in hydrogen peroxide and our catalyst 2.3 to form the epoxide over one step in one pot. This would allow us to reduce our step count from 7 to 6 back to the number of the previously reported synthesis, as well as being able to form that epoxide in that that chiral epoxide. Where this step, which I was talking about earlier, 2.2 to 1.3, is done through one step rather than two in our previous route. And it also avoids titanium 4, which is pretty dangerous, and which also allows for greater scalability. To get this forward-facing epoxide, this prolidine catalyst first forms the same complex that you saw in the aldol condensation earlier, where it forms a major product of this way, where the hydrogen here on the prolidine is not sterically encumbered by this hydrogen here on the olefin, which is the minor product. Then, with the addition of hydrogen peroxide at the most nucleophilic site, it forms these two bonds, which then closes down to form the epoxide, with the major product being our desired epoxide and our minor product being the backwards facing inactive epoxide. Following that through hydrolysis and then reduction, we get our desired epoxide with the alcohol. Alongside optimizing synthesis, this one-pot sequence has never been reported before. And to see the effectiveness of this one-pot, we wanted to define a substrate scope of what this reaction works on. So we are going to test on long alkyl chains such as Medicinal, multiple primary aldehydes such as malondialdehyde, and test this reaction in the presence of other functional groups such as ethers, alcohols, amines, and sulfonyls, and many others. Alongside that, we have been working on computational modeling. As I said before, you can see that the model earlier was not covalently binded in the pocket. And to do this, we need to use a bit of induced fit docking. Our molecule binds to our enzyme in an induced fit fashion, where it first initializes, then it goes through the transition phase and reaches its final complex.
Yeah.
We're currently working on fixing our docking model, as there is no crystal structure of CPT1 made yet, and therefore we're still troubleshooting this. But through docking, we're able to see the difference between binding affinities between CPT1A and CPT1B, where we want higher selectivity for CPT1A, so we can we want a lower binding affinity for CPT1A, so we can have higher selectivity for CPT1A, which would lower off-target toxicity. As you can see on the left is some preliminary data from our Schrodinger runs, where you can see that there are some differences between the glide scores or docking scores between CPT1A and CPT1B. We would want a docking score lower for CPT1A than CPT1B. So through this, we would be able to design our analog library and choose which analogs would be the best to synthesize. In the future, we're planning to optimize our formal route further to easily synthesize our analogs and define a substrate scope for our aldol condensation Luche reduction one pot, as well as finish our induced fit docking on Schrodinger to finalize our analog library, as well as colorimetric assays to test the efficacy of our analogs for CPT1 inhibition. I'd like to thank my fellow CPT1 project members, as well as my advisor, Dr. Njoo, and our collaborator, Dr. Chen. And a big thanks to ASDRP for allowing us to conduct research. And thank you. If there are any questions, I can take.